Okay, you guys should have gotten your tests back in lab on Monday, is that right? Okay, and then you have, I guess, a regression lab that you guys are, not I guess, I know. Okay, any issues? Anything? Yes?
Is there any way to adjust like the scales or those stuff in the scatter plot?
In the scatter plot, yes, you can change your x-axis limits with the commands xlim and ylim. Does that not work, or?
I tried that command, but it says something like invalid argument or something like something about argument.
Invalid argument. Let's see. Too much. Invalid argument. Okay. Is that?
Like it's something about our argument. It's not. I don't know.
Okay. Let me. You got to put in the limits with. Is this too loud? No, it's okay. All right. I just feel like I'm talking inside my head. You would have to do xlim is equal to C0, 100, or whatever it might be. And that's not working?
Yeah.
You would put this inside the, you would have plot, and then x, y, and you'd have it like this.
Yeah, it should be the plot ff and x equal to something like hits, and y can be like home runs.
Okay.
And yeah, let me see.
So you might, you put something like plot, whatever your data set name is, baseball, $, at bats, baseball, $, runs, and then xlim equal to C, whatever appropriate numbers would go there. And you're entering it like this, but it's not working?
Yeah.
Okay, well, sometimes that happens. If you have issues, you can try emailing me or the TA, and we can attempt to help you out. Okay, well, today we will continue our lectures on regression, correlation. So on Monday we left off just talking about creating your regression line. And so the regression line will end up in the form y hat is equal to b0 plus b1x. You plug in x, and then it spits out a y hat. If you have an actual data point, okay, so the actual data point might be x comma y, and you can compare that to x versus y hat. Okay, the x, y hat, this will be along the line. So the difference between y minus y hat, this is what we call the residual. And it's the difference between the actual data point versus our prediction for the data point. Okay, so the residual is equal to the actual minus the prediction. Okay. And I think I left off at the end of Monday's lecture saying that when we look at the residuals, we don't want to see any kind of pattern in the residuals. So after performing regression analysis. So let's just explore a few possible examples here. So if I have dots like this, and this is our regression line, our line of best fit, just with these 4 data points, these would be my residuals. Okay, so if I create a plot of the residuals, so this would be the x or the fitted value of y versus the residual. I have a line at 0. And so the first one is just slightly positive. And then the second one is a bit negative. Technically, I would not have these vertical lines. I would just have the dots. That one is positive by a little bit, and this one is a little negative. Okay, so I hope we can see this going from our scatter plot with best fit line. And this would be our residual plot. And what we see here is that, well, there's only 4 data points, okay, but the general idea continues to hold. We should not see any pattern. On the other hand, let's say our data looks like this. Okay. And so my line of fit would go something like that. Okay. What do you think the correlation in this plot would be? The correlation being the R value. The R would be what?
Positive.
Positive, and what do we expect? Strong or weak or what?
Strong.
It would be pretty strong, okay? So we might see something like 0.95. Alright? However, would linear regression be appropriate? No, okay? Because we see that by looking at the scatter plot, we see that we have a shape that's not linear. Okay? So linear regression is not appropriate. Data does not fit a straight line. Okay. Even though my correlation is very high at R equals 0.95. Okay, so the value of R, or even R squared, if I square 0.95, I would get something also very high. Even if it says a lot of the variation in y is explained by x, and it's true, a lot is, linear regression is not going to be our best fit here. Okay, and if I created a scatter plot, and not a scatter plot, this is the scatter plot. If I create a residual plot, I will definitely see a pattern in the residuals. So the first one is slightly positive, and then I would get a sequence of negative residuals like this, and then I would have a few more like so. So maybe this is a little exaggerated, but this would be, we would see a pattern in our residuals here indicating that there are deficiencies with our model. Okay. And maybe we can see that already with the scatter plot, but in some cases it will not be completely obvious, and the residual plot will give us a better idea of whether or not there's a pattern in our residuals. This chapter 9 in the book is called Regression Wisdom, and it's all about just things to be careful about, okay? Because regression is a very useful tool. Now, even linear regression in its most simple form, it's a very useful and powerful tool, but it can also be dangerous because if you didn't create a scatter plot and you saw r equals 0.95, you might assume, oh, linear regression is great, and we go forward with it, but then your model would be incorrect. Okay. Other things to watch out for. We have points known as leverage points and influential points. Okay. So if I were to create a scatter plot, and on one axis I have someone's shoe size, and on the other axis I have their IQ score, or SAT score, or whatever. Okay. Would we have, what do you think the correlation or the R would be? 0 or something very close to 0. If there's any kind of pattern, it would just be by coincidence. Okay? So if I create my scatter plot, I would probably just see a whole bunch of points. I would have people with big feet, so this would be shoe size. And this would be IQ or intelligence, however we might want to measure that. So we would have people with little feet with high intelligence, people with little feet with low intelligence, people with big feet with high intelligence, people with big feet with low intelligence. Okay? And if we were to try to create a scatter plot, getting some feedback here. From the scatter plot, we would see that there's no real relationship. Okay, and any correlation will be either 0 or very close to 0. Basically, any deviations from 0 would be a result of coincidence. So my line of best fit will probably be something like this. Okay, this will be my best fit line. Okay, that good with everyone? So if R were 0, then my best fit line would have a slope of 0. Okay. On the other hand, what if I throw in a person with very large feet? Okay. So let's say someone has extremely large feet, and this person had a very high IQ. Okay. So we have a point right there. What would happen to my correlation? It would suddenly become positive because over here is my mass of points, and the correlation would want to try to accommodate this point, and so my line of best fit would probably change to something like that. All right. So this point, this is an influential point. Okay. Because its inclusion significantly changes the results of my regression, including this point changes the regression. And if we did not create a scatter plot, we would have no idea that this is going on. Okay, so by seeing the scatter plot, we might say, oh, wait a second, I got this outlier here, and this is influencing my regression. And if that were to happen, then we might want to exclude this person from our analysis because we recognize that it's throwing things off. Okay, part of the reason why this is influential is because it has what we call leverage. Okay, so if we look at the mean of x, just for these points, the mean of x would be somewhere around here, x bar. Okay, but then this guy is very far from the mean of x. So its distance from x bar is known as leverage. Okay, and so points that are far from x bar have leverage, okay, or more leverage, I should say. Leverage is neither good nor bad. It's just something that exists, and but it can change the results of a regression. Okay, if this person with very large feet happened to have a very low IQ, and we did not include this one, then our analysis would change to something like that. Okay, so the high leverage in this case greatly influences our regression. On the other hand, if I have a whole bunch of points like this, okay, and my overall regression looks something like that, and let's say I include an outlier way up here. Okay, so this is significantly different from everybody else. But does this influence the regression analysis very much? No, it might pull up the line just a tiny bit or something. This would not be as influential. This point does not have leverage here, okay? Does not have much leverage. Okay, so its inclusion or exclusion does not significantly alter the overall regression, but this point is an outlier. Definitely an outlier. And then you might have regression that looks like this. So you've got some kind of, it looks like there's definitely a pattern over here, and then you have a point right there. Okay, and then it seems like, oh, this is great because, well, my illustration's not so great, but it might seem like, oh, Well, the pattern that we established down here seems to be confirmed by this point out here. Okay. This is a little dangerous, though. Okay. So this would be a leverage point, not influential, because it appears that including or excluding this point would not change my overall linear regression. Okay. Okay. But there's this does not necessarily mean that everything in between would actually follow the line either. Okay. It might not. We haven't collected any data in that region, so it's hard to know exactly what happens there. Okay. The actual trend could actually go like this, and this could just be a weird point that you happen to collect by coincidence. We don't know. Okay. So that brings me to my next point, that whenever we perform linear regression, we should not extrapolate beyond the regions where we have collected data. Okay, so extrapolation, this is discouraged. So the idea is, perhaps we have collected data and the data looks like this, okay? Or I should put in a little bit more scatter. And so that would be a great model. We'd probably have R is equal to, 0.98 or something, and y hat is equal to b0 plus b1x. And we could plug in values of x to get predictions for y or estimates of y. We then might be tempted to use the linear regression model to say, okay, well, what would happen if x was all the way out here? Our prediction for y would then be here. Okay. However, we don't know if the linear regression model holds outside of the zone where we have collected. Okay. The model is valid. Collected data. So, a silly example would be perhaps you are looking at the heights of children at an elementary school. Okay, so you plot the age of the child, and elementary school starts around 5 or 6, and you just keep going. Something like that, and then you plot the height. And what we would see is this general trend that older kids are taller than younger kids. Okay. So we might be tempted to then extrapolate what would the average height of a person be at age 30 or something, okay? So we could extend this out to age 30, and we might be predicting that people are going to then be 8.5 feet tall or something, okay? So if we use this, if we use the model to make predictions for people aged 30, okay, we would predict something like 8 feet tall or whatever it would be, okay? All right, and we know that would be a silly thing to do because we know people keep growing until they're, I don't know, 18, 20, I don't know, some people still keep growing after, very slightly after age 20, but generally once you reach 20 or so years old, you stop growing, you don't keep growing, and so the true model would go something like this. And so we do, it would be wrong to continue extrapolating to people who are age 50 or 60 or 70, because then we would think that everybody keeps growing, okay? But you could see, if you knew nothing about human height, and you just saw the numbers on a piece of paper, you could see that every single year, the numbers that you are observing are getting larger, okay? So if you did not know that these were in reference to the heights of children, you could see how somebody might be tempted to continue extrapolating, because at this year all the kids were this height, or all the, the numbers were this region, and then the next year the numbers got bigger, and the following year they got bigger, and they continued to get bigger for the last 8 straight years or whatever, okay? And it might be tempting to say, okay, well, this pattern held very true for the last 8 years, very consistent, so we would want to extend this into the future, okay? That would be a bad thing to do because the linear relationship may not necessarily hold, okay? So, predicting the future is something very difficult. We have no idea what will happen in the future, so who knows? Okay, maybe the pattern keeps going straight, maybe it levels off, maybe it takes off. We don't know, okay? A lot of times when we're observing data, we're only observing data in this zone right here, and we have not collected any data from the far reaches of the future. So, so watch out for that. Okay. And other warnings for regression is that correlation is not causation. And I think I've already mentioned this, but it's worth mentioning again. Correlation is not causation. If you see 2 variables are correlated, there's probably some kind of relationship. There's probably something linking the 2 together. However, that relationship may not necessarily be the x variable causes the y variable, okay? So x and y are correlated. Okay? There's very likely to be some kind of relationship, okay? Okay. But we should never conclude that x causes y. Alright? And I say very likely because it's also very possible that x and y are correlated just from coincidence alone. Okay? So it could just be coincidence that you've collected data and X seems to follow this pattern and Y also seems to follow that pattern, okay? So X and Y could be correlated from coincidence alone. Okay, so did I do reading level and household appliances? Okay, so true study, they looked at a whole bunch of different households across America, and they looked at different things related to the reading ability of the children in the house. And what they found, surprisingly or unsurprisingly, however you take a look at it, is that if you looked at the number of household appliances, so that would be dishwasher and, I don't know, toaster ovens and things, all of these, however many household appliances there were, they found that homes with more household appliances had children that read at higher levels than homes where there were few household appliances. Okay? So there's actually fairly strongly correlated. But does that mean household appliances influence the ability to read? The ability to read. Okay, obviously not. All right, and we can probably conclude that reading ability, for whatever reason, is correlated with income. And in general, homes with higher incomes generally have children that read better. Okay, and even then, so we might say, okay, well, the underlying thing is not household appliances, but income. But does that even mean that income causes better reading levels? No, this is a very complicated issue for which I don't know if there's a very, very good answer, but we do know, and we can all, I think at some point you can just say, oh, well, things are correlated with income, intelligence or reading levels or grade things. A lot of these things are correlated with income, and we see across the board that generally families of lower income have students or children that perform poorly in school, and families with high income generally have students that perform well in school, although that still doesn't explain why. Okay, it's a well-known and established phenomenon that we observe and no one will dispute, yet what exactly, why does earning more money suddenly, why is that associated with higher performing students? That's a lot more complicated, okay? Access and all of these things and social circles, all of that come into play, but it's hard to say. Okay. So anyway, correlation is not causation. All that to say that. Okay, let me do a few things on the computer with your lab. You got a few exercises in the homework. I'm skipping chapter 10. Okay, so come on Friday and we are going to cover we're going to enter chapter 11. Chapter 10 is all about transformations to your variables. Okay, and so we talked about maybe your data fits something like this, okay? And in this case, linear regression would not be appropriate. Chapter 10 is all about transformations, and we would say, okay, in this case, maybe we should take the logarithm of all of our y variables, and then that would change the shape of our data, and then we could plot them, all right? So it's all you're doing is you're just either taking the square root or taking the log or whatever it might be. It's just applying a transformation. I'm not going to test you guys on it. if you're curious about it, you can take a glimpse in chapter 10. It's exactly that. Okay. All right, let me just do a few things here. We will fire this up. Are the I don't know, are the labs going better, or is it still terrible? Still terrible? What's terrible?
R Markdown.
Huh? R Markdown? Okay. If R Markdown sucks, don't use it. I only put it there to make your lives better. But if it's making your lives worse, don't use it. Okay? We'll just leave it at that. But I don't want to set up Chrome. Let's see. But RStudio is working okay? Yeah. Okay. I always forget my email address for this thing. This is not right. Bruinman. What is that? Okay. I hope this is correct. Okay, and then what did I have here? There's the clock here. Okay, so we will load this data. Well, is this, maybe I don't need to do this, but, okay, so we have MLB runs and at-bats, right? So we can do plot. Oh, shoot. Did I not load the data correctly? Oh, MLB 11. All right, this is great. That's why it's index. No, just screw that up. All right. Using. Okay. Okay, and so you can. Well, there's several ways we can do this. One is we can create a linear model. Where we have runs as a function of at-bats, and I can ask what is our model, and it looks like this. And I can do AB line model, and that fits, should fit. Something just happened here. Let me try that again. Okay. So R can produce a bunch of these things. You probably don't have to do all of this. You will create the, in your directions it talks about making a linear model. And you can create the summary. And then it also, I don't think you create the plot itself. But if you just ask, give me a plot of the model, for some reason my plots are not being produced. Okay. But anyway, this is a residual plot here in of itself. And it shows, this is what, here it's telling us what we predicted, the value that we predicted. for the number of runs, and it shows us the residual, okay? And so if we look at this, it looks like there's no general pattern. It tries to kind of fit maybe a pattern if it sees one, okay? And then so here we have this red line, and we see, okay, well that's not so, it doesn't look like there's something incriminating about this, this red line here. Okay, so that's our residual plot. The other plots create, this is a normal QQ plot for the residuals. Okay, so this is, I didn't talk about this, but one of the assumptions is that the residuals themselves, the size of the residuals, should come kind of from a normal distribution, meaning you should not have most of your residuals should be close to 0, okay? That will be the bulk, and then you'll have some residuals that are larger than that. But you shouldn't have anything with, in terms of z-scores being far too large or far too small. Okay, so do the residuals fit a straight line? Not exactly, but at this point I would say there isn't a whole lot that would cause me concern with this normal plot of the residual values. And then this last one I would not worry about. These are all just parts of different theories and diagnostic rules regarding regression. And so here they're talking about residuals and leverage and all of this. We're just doing basic linear regression here. Okay, let me see if I can find a better, another model. So if I do names. Let me just make one more model with the relationship between runs and something not related, stolen bases. Okay, so let's plot. Okay, so we see something like this. Not a whole lot of correlation here. I could ask for the correlation between these two things. And the correlation won't be exactly 0 because just by coincidence or whatever, it's close to 0 but not exactly so. And then I could create the model, and I can ask for the plot of the model. Okay, and so, well, this was not, I wanted to include I forgot how to do this. I apologize. Okay, well anyway, this demo was not as insightful as I wished. But, okay, well, I probably won't ever do this demo. Well, there is, I want to include some leverage points and show how that influenced the regression, but I did not prepare the data set, and then it's too much work to try to add one data point at this point. So anyway, we'll just end right here, and we'll see you guys on Friday. I hope this week's lab is not so awful, and again, if our markdown is giving you too much trouble, just skip that and copy and paste your stuff into a Word document.